Again. What's up, bro? Sure.
已解锁，请取出话筒。
We will wait a few more minutes. Hello, Manish. So before we start lectures, hello, testing, 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 test, 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 test. Hello, hello. I was like inspired by what the Qi Yang said last time, right? Say USD to maybe MYR is just a unit change, right? Like KM to meter, right? Seems very reasonable. I was convinced at first. For example, if I say I run 2 meter, right, it's actually equivalent to that I run how many km? Ah, don't tell me you don't know. 0.002 kilometer. But then, if you take 1 ringgit, please go US and use it. You have to do currency exchange actually. So you need to actually go to a center or what to change your money before you can use. Otherwise, they won't accept. Okay, I didn't go so far actually. You just go to Brunei, just go to Singapore. They won't accept RN1. The retailer won't accept RN. So this is the problem here. Your me- you cannot store your distance in meter, but without in case. But you can store your money in different currency. So this is the difference here. Although it's just a unit change, but in reality, this is what happens. Okay. 啊，但是这样子讲到，对。 So actually this is a reason of how to say. I think this is about theory and practical already. So in reality, what do you do with this unit change, right? So I mean, uh, this kind of practical, right, is sometimes not really emphasized emphasized in the curriculum or teach class or what. Only when you really need to use it, or you need to realize that, oh, I have to go here, change my money or what. Maybe now it's even easier, right? Because touch and go, whatever, you just Alipay. You go China, you don't need to change currency already. Yeah. So everything made easy. Maybe in future, there's no distinction already. It's true, maybe. Yeah. So, mm, so because we are kind of a theoretical person, right? So I think it's important that we be a little bit more practical. And this is actually why I come back to Malaysia actually also. Yeah. Because I was like studying for like 28 years non-stop. Non-stop or really non-stop. I didn't work or what. Maybe got part-time, but those are like not really experiencing, but then um try to experience more like what I have studied so that this knowledge makes sense. Also, like what I told you last time, right? About you asked me about the Methodism and constructivism thing, right? So I was trying to like understand what I was studying actually before, because actually I met obstacles in research because I've run out of idea. I run out of question actually. So I read something, I don't know what to ask. Like you, I like you actually. You read this course, you don't know what to ask, you don't know how to ask me, you don't understand, you don't know how to ask me. It's the same. I also have this stage. I also have this stage. I don't know how to ask. I don't know how to ask my supervisor. I run out of questions. Yeah. So what to do? You just keep reading. No choice. Because this something is out of your imagination, out of your experience. This thing. And so you just make it your experience first, and then only you can ask new questions. Okay. 哎，思慧，你的朋友哎，有的。Okay. Right. Uh, Another thing is, quiz 2 is here. So later break, you can come and look at your quiz. But then the result I think is better than last time. So in this class, I want you to focus whether you got improvement or not. Okay, so you just keep improving. That's the main goal for you in this class. Okay. Um, do you think that you are not good enough or not? Would you have this kind of like viewpoint? Any one of you? Or you think I'm good, very good, and the best? What do you think? Huh? Ping Jie. I think you have a lot to say. No? What do you think? You think you're good or you not good enough? Huh? Or you happy with what you have now? Oh, you're happy? Oh, yeah, okay, good, very good. This kind of person, very satisfied, easy to satisfy. Okay, so my viewpoint is it's okay that you are not good actually, but you need to keep improving. That's the most important. Okay. Yeah. But then if you are satisfied, then I won't kacau you. You're happy, you stay where you at. Okay. But then if you think that you are not good, but you want to be better, you just improving. That's it is important. So the idea is like this. Okay, maybe you are just 8. Maybe you are like 40, right? So someone is 80, right? But then if you can slowly add by 5, slowly add by 5, then one day you can like achieve better. Right? Right? You learn induction, right? Then you learn Archimedean property. Right? So you slowly you will surpass this person. Right? I mean, like given this person is like really slow. But then no matter what this person is, the most important thing is what you gain here. Okay, the most important thing is what you gain. Okay, it's very important. Okay, your gain is important. It's like, for example, like in Australia, like when I study, right, I think I'm the most stupidest person. I am most stupid one, right? Everyone, my classmates say something or like my teacher say something like I don't know what they are talking about. So this I found out that this is a very important skill. Okay, very important skill in studying actually. You need to try and understand what people say, understand what the book say. Okay, it's not like you just get some main point and then answer question. That's it. Okay, so you need to try and understand what's the content of the lecture notes. My previous students are also complain. I think like what some people here complain also. Maybe it's hard to read lecture note or what. Then after they study revision for final, they think that, oh, actually your lecture note is like a storybook. What does it mean by storybook? You know, what constitute a story? Huh? Link, very important. Good. So there's a link there. There's a logic there. This one go to this one, go to this one, go to this one. Yeah. So it's not saying that every some part have to be very important, but then all part have to be important. Understand? You want a forest, you cannot say I don't have flower. You cannot say I just have trees. You must have some small animal also, small insect also. You cannot say these things not important. If you take away this, for example, when I go to Australia, right? Australia, the climate is very different. Right? It's dry and cold mostly. And then if you drive along the way, you see the mountain. There's no tree one. You feel like this is not forest. This is not the forest I saw before. Because if you drove along the Malaysia highway or road, you'll see a lot of tree, right? And then the fern growing out like that, a lot of grass. But Australia is not like that. It's very dry. It's like just a single tree like that. There's no grass also either. Right. So if we are missing this element, right, then this is not the full story. Okay. Okay. Does it make sense? Does it make sense? Okay. 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 Cool. So there's some extension from your quiz, right? So some of you will write like I want to find n plus 1 that's greater than 1 over epsilon. And then you go find n greater than epsilon, 1 over epsilon first. And then you can get n plus 1. Okay. Second is you go and find n. So you go find, so okay, maybe I should write in this way. So your goal is to find this. First kind of person find this, and then second of person find this. Do you think there's a difference here? You think there's a difference here? Can you give an example to demonstrate the difference? Sure. It's possible to get negative number there, right? Okay. So let's consider, I think, epsilon equals to 1 is already enough. If you go and find n greater than 1, what kind of n you can get? N like 2, 3, 4, like that, right? Okay. But then your n plus 1 becomes what? 3, 4, 5. No? Makes sense, ma? 3, 4, 5 still greater than 1. But how about the other one? N is just greater than 0. But then your n is could be 1, 2, 3, 4. Then your n plus 1 could be 2, 3, 4, 5, like that. So what did you see? The second case here include one more extra possibility. Okay, so you need to be careful when you write these down, which one you want. Okay, does this extra possibilities uh, works or not? Sometimes it doesn't. So you need to be careful. Okay. Or sometimes you miss out some possibilities. And so be careful on what you want to find. Okay. Or when you want what you want. Okay. Okay, this is for this part. Okay, the other part is about from your discussion in your tutorial, right? So in tutorial, we have a set of AN, and then some of you see it as a sequence. Okay, these two things actually is not too far away from each other. You know why? What's the difference between these two things? Any idea? One, I viewed it as a set. The other, I viewed it as a sequence. Sequence, last time I say that it's a function from n to r. So n there, we regard it as the order. There's an order there. So A1, after A1 is A2, A3, A4, A5. But set I don't really care. I can mix them. Or Malay we say campur. I don't care about the order. Okay. Does it make sense? Okay. So I don't care. So but then there's a idea that comes in, right? If it is bounded above, then we can find a least upper bound. Okay. On the other side, sequence here, we have something called limit. Right. So try and write down the definition. And then we realize that these two things looks very similar also. Okay. So supremum is to show something is a supremum, you need to show that for all n in n, an is less than or equals to the sup of an. Okay. And then second, for all epsilon greater than 0, there exists a element in the set of an such that A is greater than sup of an minus epsilon. But then if you rewrite this, what is this? This is just a sup of an minus a less than epsilon. But limit, for every epsilon greater than 0, there exists an n in n such that if n small n greater than the capital N, implies that an minus L is less than epsilon. But then this is just saying that an minus L is squeezed between epsilon and minus epsilon. Okay, so here's see what's the similarity here. We have both of these, there's something bounded. And then the term that heck is element in the set of an or the sequence. Right? And then with some fixed number here. Some fixed number. Okay, one is L, one is sup. But then the position is different. Why is it different here? Because the sup an here always greater than A. So if it turns out that this limit is always greater than an, then you can do it the other way around. But then we have two possibilities, right? So it can counter for both. So what does this mean? This means that if this an here, right? If this an here is bounded above, and then if it is non-decreasing, actually this sup is the limit. You won't get the other side of the inequality. And this is actually the content of the monotone convergence. Yeah, the sup is the limit. If you are non-increasing and then you are bounded. And then the other side will give the bounded below non-increasing. Infimum is the or this two side. Does it make sense? No question. Or should I write one more thing here? Maybe I'll write one more thing here. This is an minus L less than epsilon. And then the other side you get L minus an less than epsilon. Okay. So one side can get you the supplement, the other side can get you the okay. Any question? Question? Any question? Okay. If no question, then we will continue with Bolzano-Weierstrass theorem. Later I can show you a video on Weierstrass. I mean, people talking about Weierstrass. Okay, so what's the statement of Bolzano-Weierstrass theorem? Anyone can recall? What's the statement? Okay, one more detail missing. It's not always true, but then there's one more detail you need. You cannot simply take a sequence, but that sequence have to be living somewhere. No. I mean, like there's one more condition on your sequence. Try read again. There's one very important detail. Read your statement. Read the statement. Read the statement. One more detail. Okay, so he said that every sequence have a convergent subsequence, right? In where? Very important. What kind of interval? Not every interval works, no? Because real number is also an interval. Real number is so big. What interval is very important? What kind of interval? Two adjective. Read the statement. Two adjective. Very important. What kind of interval? Who else can help? Yes, close and bounded. Okay, very important. Okay, this is what we will call compactness later. So every sequence of real numbers contained in closed bounded interval has a convergent subsequence. Okay, so if converge, right, you can ask about limit, right? So what do you think? Where the limit should live in? Where's the limit? Where's the limit? What do you think? Where's the limit? Where's the limit? Huh? Having limit in where? Where's the limit? In that interval. Okay, you won't go outside one. Okay, so uh that's why we say that this kind of interval is close. Maybe to you, close is just a bracket, right? But then close would mean something about limit. Okay, that's why we put the square bracket. Okay, yes. Here's more. Oh, okay. Sorry, this is just a shorthand notation. I'm just being lazy. Every sequence. Yeah, I mean like sure. Okay. Sorry. Okay, sorry. I'm just trying to direct translate English to simple only. But then what I meant is this. Yeah. How about like this? But then for this class doesn't matter because the sequence always puts in real. This class doesn't. Okay. Now okay. Okay. Okay, very good. So I promise you to prove in the second way, right? So this is the second proof. Which we will use MCT, okay, monotone convergence theorem. But then before that, we need to define something called a vista point. So we define n in n to be a vista point. So it's a natural number, this vista point. It's a natural number of the sequence an if am less than or equals to an for all m greater or equals to n. So what does this mean here? So after this point, right, all the point beyond it will be small, equal. You know what is vista is? You can try and search what is vista. What is vista? I think in Chinese it's called something like a guang wan tai. Guang wan tai vista. You can try and search. Okay, so does it look like a guang wan tai? It's like a sang feng, I guess. What did you search? Did you find what's vista? What's vista? What's Vista？错，你找到什么图片？What？孩子哈，你找 Vista English 啊？English。What's Vista？远景哈，远景哈，可以看到远远啊，对不对？Okay. So, if you imagine what this vista point should be, it should be something like this. So, we draw some example for you. So maybe I draw a sequence, and then you can tell me which points are the vista point. Okay, which are the vista point here? This one. This one, fourth one. 1, 2, 3, 4. What do you mean one of them? Left more. One, two. Left, right. Left is here. 1, 2, 3, 4. Right. You said fourth left. Oh, leftmost. Oh, okay, 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 okay. Okay, 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 okay. Why I keep hearing the four? Okay. Yeah, yeah, right. Okay. So if you stay here, right, you can see that everyone is stay here, everyone is below you. But if you stay here, someone is higher than you. So it's like a vista. Okay, so there are two possibilities. Okay, so one possibility is there are infinitely many vista points. Second possibility, there are finitely many. Okay, so we will break into two cases. So if there are infinitely many, right, then you just take these vista point as your subsequence. Okay, and then what do you do here? So you can see that this vista point is always non-increasing. Okay, because we are making sure that everyone is below you. And is it bounded below or not? Is it bounded below? Bounded below by what? Huh? How do you know that Mosler right exists? I'm just keep going down. The very important property that we forget just now is what? No monotone, no monotone yet. Monotone is already like inferred by this choice here, non-decreasing. But then, where is this sequence live in? Sequence live in where? Close bounded interval. Meaning what? It is bounded above and below. Okay, right. So it's non-decreasing and non-increasing bounded below. So by monotone convergence theorem, the limit exists. Okay, good. Okay. But then you need to show the limit must live in the closed interval. But then this is a similar argument that we did before. How about finitely many cases? How about if there's only finitely many vista points? What could you do? What could happen? What could happen? If there are finitely many, what could happen? What could the sequence look like? One possibility is like maybe what could it be? Finitely many. What do you think? What do you mean? Are you going to draw that? How how are you gonna draw? Huh? How are you gonna draw that? One, two, two going up. Wait, what's the height? What's the height? Right. Okay, when n equals to one, what is it? What's the value? Zero, okay, and then negative one. So you go down. And then 1.1, so you 1.1, okay. And then negative 1.11. Okay. And then 1.111. Okay. Okay. So you say that this one has finitely many vista points. Why? Oh, no vista point. Yeah, sure. Yeah. I think there's like, I feel like there's no non-trivial, non-zero finitely many vista point. It's kind of impossible, I think. Okay, but anyways, okay. So this is a case that there's not no vista point, right? Okay. So actually, what do we do here? If there's no vista points, meaning there's something that keep going up. There's something that breaks the vista point rules. So how to break the vista point rules? The sum am should be greater than that am there. Okay, so there's something that's increasing. Okay, so you can pick up a subsequence that's non-decreasing, for example, or increasing. Okay, increasing if it's bounded above. So by monotone convergence theorem, the limit exists. Okay. Yeah. Okay, so the idea is like that. I guess the full proof is inside the notes. Oh, actually I did one in my notes. Okay, very not tricky, but then finitely many. So I guess this is what I did. Like this, and then you like this. Okay, so can you find the vista point or not? Maybe my limit go here. Can you find my vista point here? So there's non-trivial vista point here. Again, leftmost is the vista point because everyone calculated it at this point. And then the other one, maybe you can pick this two. And then maybe also this guy higher a bit. Okay. So can you see the convergence subsequence here? Can you see? In this case here, what's the convergence subsequence? Huh? The limit? No, I looking for sequence, not limit. Maybe you can pick this guy, right? Is your convergence subsequence. Okay. So you are picking the point that cannot make you find vista point here. So they are okay. And then it is bounded above by D maybe. So the limit exists here. Actually less than D. Okay. Your question? Question? No. Okay. In that case, actually I draw some examples. in my notes, right? So there's one example that looks like this. Basically, I built a pyramid, kind of a pyramid. So something like this, like this, like this, like this, like this. Okay, so can you write down the formula for this? Maybe this, the middle point is C plus D over 2. Okay, so what I did is I defined AN to be D, C, and C plus D over 2 if N is 1 plus 4K, and then if N is equals to 2K, and then if N is equals to 3 plus 4K. So basically, I split it into mod 4. So 1, 2, 3, 4. Okay, so if I use the infinite, uh, what's that? Pigeonhole principle, what do you think? What kind of subsequence we can get here? Or maybe look at the vista point first. If you look at the vista points, right? So which subsequence you can choose here? 1K plus 1, 4K plus 1. Yes. So you are picking out this constant sequence here, right? As your convergence subsequence. I mean, constant sequence definitely conversion. But then if you use the pigeonhole, right? It could be the case that you pick up this one or this one, or three of them you can do. Okay. Does it make sense? Okay, so I mean like pigeonhole can produce these three, but then a vista point can produce the first one, can only produce the first one. Method. Okay, make sense? Okay. Okay. Any questions so far? Any question? 20 吗? Okay, if no question, we will continue. We'll continue to a new idea, what we call the Cauchy sequence. Okay, Cauchy sequence. Cauchy sequence is a very important concept, okay, in analysis. So, maybe can ask you a question. If a sequence AN satisfy the following limit here, the length between the subsequence term converge to 0. Is it true? Is it true that the sequence will converge? Huh? I mean, this is a very naive way of thinking, right? So you might think that, oh, if I get very close to you every day, maybe maybe this sequence can converge. Is it possible? Not really. You tried before. Okay, just a joke. Okay, I mean like so okay, let me draw more appearance for you this condition here. So maybe at first you are very far, right? But then day by day you get very close, or oh, does this mean that this sequence will converge? Huh? Does it mean this sequence will converge? Why not? Ln n, ln n, ln n. Is it easy to verify ln n? Ln n minus okay, ln n minus ln n plus 1, then huh? 倒反 doesn't matter lah. I mean like okay, if it matters then we just move it back. because we are caring about the absolute value. So yeah. Okay. Then what is this? Is this easy to compute? And then okay. Wow, the n conversion 0. Okay, so then this one you need to rely on like continuous function can bring limit and whatever those things you need to tell. Okay, if you can do those, then you can see that this one converge to 0. But then let's say we don't have these two, right? These twos. We can do something tricky. Let's do this. Again, is this a pyramid thingy? So what am I going to do with this pyramid? So maybe my first pyramid is like this, right? And then I slowly increase term along my pyramid, such that the consequence term will get closer to each other. But then I still keep this distance. Oh, okay. So how do I write down this sequence here? Actually, it's 0, half, 1, 2/3, 1/3, go back to 0, and then increase again. But then I increase slowly, very small, increase even smaller. But then I always keep a 0 to 1 distance, and then I come back. I think from the picture, it's clear that this is not converging. Or you can show it like how we show the -1 to the n doesn't converge. You always find some point that's epsilon away from the limit. Okay. Yeah, but then how do I make sure the subsequent distance increase? I put more terms in between 0 and 1. I can always do that because my real number is very dense. I can pick a lot. Okay. So you can see that one is using the denominator 2, right? The other one is using denominator 3, denominator 4. So I put all the fraction in denominator 4 between 0. Split into portion, n portion. Okay? Does it make sense? Okay. Yeah. The other example you can try is square root n actually. Yeah, square root n. Okay, so what's the condition for something to converge actually? Okay, so this inspired Cauchy to do this. I think it's Cauchy give one. Maybe you can check whether it's Cauchy give one. Sometimes they name it after another mathematician because they inspired them. Huh? Ah. Is it? Seriously? Okay, maybe. Wow. Maybe you can try. Wow. Maybe you can try and find that. Okay. Cauchy sequence if for every epsilon greater than 0, there exists an n such that mn greater than if little mn greater than n epsilon. This implies that the absolute value between am and an is less than epsilon. Okay. So what's the difference between this and what we had just now? Just now we are just comparing subsequent terms, but here arbitrary term after. So everyone have to get closer. It's not just a subsequence. Okay, it's not the subsequence. It's everyone. I need to compare this one with this one, any one of them. So that I can squeeze everyone together. Understand? Okay, so this can avoid what happens here. Right. You see, it's a 0, 1 here. You can never squeeze them closer. So with the Cauchy sequence, I can squeeze all these 0, 1 together so that they can converge. Okay, after some big n. A sequence, we only care about the finite limit before, but the tail is very important. Okay, does it make sense? Okay, for any mn greater than n, every one of them have to squeeze. Okay. So first theorem is very important theorem. A sequence an is Cauchy if and only if it is convergent. Okay, actually, this is a very important result here for real numbers, actually. This is only true when something is complete, when real number is complete in particular. If you put Cauchy sequence in different places, they might not converge. They might not have a limit. Okay. So let's do proof. Let's go from right to left. Suppose it's converged, then it's Cauchy. So let's write down what it means to be Cauchy. So I want to show that for any epsilon greater than 0, there exists an n such that for all mn greater or equals to n, capital N, the absolute value of am minus an have to be epsilon small. Okay. So you want to show a statement for all, right? So you need to fix epsilon greater than 0. So you want to find this n epsilon, but your goal is this inequality here. Okay, so maybe you can try and see how you're going to bound this term first, and then you can decide what is your n epsilon. Right. So what I have to fix into here? Yeah, so you need to look at your assumption. Okay, you definitely have to look at your assumption. Okay, so your assumption is what? It is convergent. Convergent means what? There is an L such that an minus L is less than. Okay. So how do you include L inside here? How do you include L here? Okay, minus L plus L, for example. So you could do minus L plus L here. So why are we doing this? Because we're gonna split it into two terms that looks like an minus L plus L minus an here. Okay. But then you can bound these two by epsilon, right? Because convergent. Okay. So you want bound by epsilon or epsilon over 2? Up to you. Okay. So you can bound by epsilon over 2. Such that the sum of them is bound by epsilon. Okay, so in this case here, how to find this n epsilon? So fix epsilon greater than 0 by the convergence of an. We can find how should we put it there? We can find what is a better way to write it? Okay, we can find m epsilon over 2 such that for all n greater than m epsilon over 2, absolute value of am minus L is less than epsilon over 2. So now fix n epsilon to be m epsilon over 2. So that for all nm greater or equals to n epsilon, which is m epsilon over 2, and then we get this. Okay, this one is equal, sorry. Okay, does it make sense? Okay, can you see why I write different SN here? because the M should be given by your conversion of your AN, and then this is N epsilon is what we want to choose. Okay, then we just choose this M. Just match, yeah. Okay, so far so good. Question, no question. Any question? No? Okay. Next. Okay, let's finish the proof and then we will break from here. And then later on I will make a very important conclusion. I mean, not conclusion, remark. So how about the other direction? Proof Cauchy proving convergent. Yeah, Cauchy proving convergent. So what we're gonna do is we will split into two parts. First is a very important result. Actually, it should be a lemma. Every Cauchy sequence is bounded. Is it clear to imagine a Cauchy sequence should be bounded? Because the tail is like already bounded by an epsilon. So kind of bounded. Last time we showed that every convergent sequence is bounded, right? Yeah. Okay. A bit similar idea here. Another one is a Cauchy sequence with a convergent subsequence is convergent. Okay. So, I mean, in this sentence, right, one part of it is already proven. Cauchy sequence must come with a convergent subsequence. Why? Who give you convergent subsequence? Do you still remember the theorem that can give you convergent subsequence? Bolzano-Weierstrass. But what's the important ingredient there? Why Bolzano-Weierstrass can give you convergent subsequence? Bounded. So the first part is bounded. Okay, once you prove bounded, then Bolzano-Weierstrass will tell you there's a convergent subsequence, and then you prove that a Cauchy sequence with a convergent subsequence is convergent. Okay, so what do we do here? Can I skip one? One similar to every convergent. Sorry, every convergent sequence as is bounded. Okay, maybe I skip this one. Okay, how about two? How about two? How about two? So what do you want to show here? Maybe let's write down what do you want to show. Okay, want to show that for every epsilon greater than 0, there is an n epsilon n such that let's give our Cauchy sequence a name an. For n greater than equals to n epsilon. So value of an minus l should be less than epsilon. Okay. So how? What's the ingredient you have here? I mean, what's the assumption you have? Before this is your goal, right? Okay, so everything before that is your assumption. How many assumptions you had? Two, right? Okay, one of them is Cauchy. The other one is convergent subsequence. So meaning what? You need to squeeze your Cauchiness and your convergent subsequence between this inequality here. Okay, how you gonna squeeze those two things inside here? Maybe convergent is the L part. How about the Cauchiness? Cauchiness is AMAN, right? So how you squeeze the AMAN inside? Who converge to this L is the subsequence. So how do you represent subsequence last time? AJ, for example, AJN. Okay, so maybe I plus AJN minus AJN inside here. Increasing function, right? Okay, so from here, what can you see? How many N you need to choose here? Capital N involved. Okay, so if you can make this 2 less than epsilon over 2, then you are good already. Okay, so how many choice you need to make here? How many choice of N? There are 2 parts to control, right? So you need to choose 2 things. Okay. So how to choose? So again, fix epsilon greater than 0. Since your sequence is Cauchy, that means what? You can find a N of this Cauchiness, epsilon over 2, depending on epsilon over 2, such that for OMN greater or equals to this NC here, you can make sure that the distance between AN and AM is less than epsilon over 2. The other one, second assumption, because we know that there is a subsequence that converges, let's say, to L, then there also exists another N for this limit here, also depend on epsilon over 2, such that for Jn greater equals to N, greater equals to NL here, what do we have? We have the absolute value of AJN minus L is less than epsilon over 2. Y greater than N. Why Jn greater than N? Yes, Jn is an increasing function. That's right. So I think we make it a lemma here. Have you read? Let me think. Greater or equals to. Wait, what's this lemma? Let me see. Yeah, I think it's like greater or equal to. I think the lemma we proved last time is greater or equal. I think it's greater or equal. Greater or equal. Yeah. Thank you. It's a greater or equal to. Yep. Greater or equal to. Okay. Yeah. Okay. So there are 2 N here, right? Which N do you pick? Which N do you pick for this conversion here? Which N you need? NL or NC? The Cauchy N or the limit N? Which one do you need? To make sure both less than epsilon over 2. Yeah, you need to pick the maximum number. Okay? Does it make sense? Okay. Any question? Okay, so what's the moral here? The moral here is if you know, okay, where your subsequence converges, then this Cauchy sequence will converge to the same place. Okay. Even though okay, so So the content here is if a sequence is Cauchy, if only if it's convergent. So the problem here about Cauchiness, right, is the limit is not built into this definition. There's no L here actually. There's no L here. So it could be the case that you converge to something not inside the set. What can you imagine? You can imagine this actually. You can imagine this. So what is pi? Pi is 3.1418哈。慢点，sorry，慢一点，我们不是机器人，慢一点。3.141什么15926535899。OK，好，Thank you。Okay, so a sequence you can take here is 3.14, and then 3.141. Okay, so you take this as your sequence. And then you want to ask, does it converge into some point inside the set? This set? No. Okay, no, because you converge to something pi. If not something is exactly pi. Okay, converge to the number pi. Okay, if you continue this decimal expansion, okay, it won't stay inside this AN piece here. Okay, so my point is the limit could be outside the set. And then this is exactly how we build real numbers. So we want to include this limit into our set. Does it make sense? So this is an instance of we realize irrational number as a limit of a Cauchy sequence. Okay. So last time I tell you that real number is built up by a supremum of bounded above set. So you can regard this as a supremum, bounded above set as well. Okay, if you look at this decimal expansion set, right, it's bounded above as well, bounded above by pi, and then the supremum is pi. Okay, so actually these two construction is equivalent. You can show that these two are equivalent. But then I think to prove, right, you still need Archimedean property. Because if you realize that you need the existence of the n depend on the epsilon, right? That part need Archimedean property. But then supremum construction will give you that Archimedean property. But from the limit point of view, you need to add that Archimedean property yourself. Okay, so maybe one equivalences you can see here is the least upper bound axiom is true if and only if it's equivalent to Cauchy. We say completion. So we add in the meaning we add in the limit of Cauchy sequence plus the Archimedean property. Okay. Yeah. Okay. So this part is for the epsilon less than 1 over n. Yeah. Okay. So here completion meaning you add in limit of Cauchy sequence. Okay. But then in the assignment, I asked you to show that it's equivalent to MCT, right? One side of the MCT. I'm not wrong. But then you have a choice to not do that question because I asked you to do just 60 marks out of 80. Right? But then if you are brave enough, you should try that question. Okay, completeness axiom is equivalent to MCT. There's a few equivalences that's very interesting. Yeah. No question? No, okay. Okay. This one definitely won't come out in exam, no worries. I just tell you there's a nice story here. Okay, so this is again the story about you are viewing it as a sequence or you're viewing it as a set, then different perspective. Any question? No? Okay, if not, maybe we can take a break here, break until 10:20, and then you can sign in. And then meanwhile, later I'll show you some video on mathematics. 什么？可以看 quiz，我拿出来。Yeah, please have a look on your quiz, see if there's a missing marks or not. 你是不是 cast 进不去啊？感觉又怪怪啊。Stop the Wi-Fi 问题。
一直都洗给他们，
新鲜啊。
他们洗的时候他们
OK，
不是 system 的问题。
我也是觉得。
没有，我 WiFi 老师了，但是 WiFi 哇，有我 WiFi，我那里有排骨，很给力。
是啊，就是来这个是没有错啊，不是不知道如果你要多写，
就是，因为我你的那个，我不知道你的那个 real number line 只是这一条线就可以了。我这个只是为了是，但是我有一个就是假设我有一个号码，还是取这样 set，然后我有这个号码，不是，然后这个 set 再加上它的这个
complement，对，不知道，奇怪的是那 CP 加会版，but then like 不需要这个 set 我也可以了。OK， 或者说我这个 set 可以是整个 R， 然后 complement，
这是其中一个表示。我要表示它是7怎么包也是多嘛。
OK， 我懂，这我给
你好 ，OK， 跟你的满分没有用，你的满分会被记录在话题。
是啊，是手感
啊 ，OK，
这样子，
差点赚一个，小没有给你分。
这个我的师弟看到这个大个啊，
对啊，
因为老婆啊，我的，这是我你是这边的，我当时看到之后我的，
因为你只有0.1吧？啊，就你只有0.1吧？哪里0.1？
李成玉啊，李成玉，成玉，
为什么不可以0和1？没有
摆盘，
来，我们只要0和1就可以。为什么啊？因为我最喜欢0和1。
你喜欢0和1？
不是，不是，
你是成玉，OK，
就
点到了，
我不是这个
俊汉 here， 俊汉，
你不注意一下，
俊汉好像
没有啊，这些东西，
因为我也进不去，你点得到吗？你能塞吗？
我可以进到，你没开见到，
因为我进不去，因为我进不去。
实话，什么东西？
威杰那些俊伟、子晴那些，義興 here 咯，義興那邊新呀，
所以难怪你刚才一开始你上课，所以上课前你就探讨这个东西，
没有错。
刚才你有探讨，难怪啦。
对啊，
你是看到我这样写，别人也就这样写，别人
也是这样写。I mean like 这题是没有问题啦，这题来讲是没有问题。But then 如果这个东西反方向的话，就会有问题。如果那个inequality你需要的是另外一个，就会有问题啊。对，所以意思说，我们很少会考虑这种简的号码。如果你看我的答案呢，我不会这样子去找 n。
对，因为其实可能还有一个小小的嘛，可能我们也是那个 n 是 n 大于这个 1 over epsilon，然后再大于1 over epsilon 减1，你没有写出来，要写只是没写错吧？所以过分，你没有证明。
也是
我没有写 ZFC， 我没有写 ZFC set， 我没有写什么 Excel 出来是错误。那个没有关系，我没有 proof that uniqueness of。
还有一个你比较 safe 的是，因为我们 natural number 里面没有零，那你就比较 safe 一点。因为有时候我们1 over n 嘛，你就比较 safe 一点。你懂我意思吗？对啊，因为我们 natural number 里面没有零。
但是如果 natural number 有零的话，
你就
这样子做不就 OK 哦？因为 n 等于0的话，0加1等于1，然后就可以divide了嘛。
假设啦，假设你是真的是 n 呢？假设你真的只有1 over n 在这边，你就比较危险了呀。
直接有看1 over n 发生。
所以如果能的话，就尽量避免这种有碱的东西。
这么有钱，你不要把点什么部分你用加回去呢？
因为我 realize that 其实在这个 case 其实可以 work，只是说它 in general 有时候会有问题。
你这个情况你可以大于1 over s 大于1 over s 减去嘛？
你那样子找也可以啊。因为这个不会卷。我们很怕这种negative的东西。对。反正 in 这 case OK 啦，就所以就可以。
这边我为什么加零针？我笑的心这边不临时加的。在挣扎。你会这里不完整。
你先。好，还好了，这个还没这个 obvious 比较 obvious 一点。可以。
你看到前面的这个，
有看到，我看到。你能塞吗？因为我塞不到，
因为我可以取，可是你没有开到。
对，我开不到，我进不到。
我觉得是 start 5分
是我的问题。
我觉得不是你的问题，我觉得是 start 5分的问题。如果有任何问题，我们全部怪学校就可以了。跟网络有关系，全部怪学校就可以了，不需要怪你的这个错还是什么。
好，我点名了。不过我帮你们点了啦，我帮你们点了。OK。maybe 来给你们看一下为什么你们今天要学 epsilon delta 的东西。
Okay, they're technically gates, but just imagine that you're a student here at Humboldt University and you're taught by the one and only Carl Weierstrass. He's the father of modern analysis.
所以你等下可以看一下为什么我们今天学 epsilon delta，能声音吗？说，对，我没有上哈。Okay, today I cannot sign into class so you cannot sign in as well because the system down for me. 刘解是哈 ，It's down for me, not for you because now I can show you 来，我不能开，我帮你们点 ，OK， 你们可以sign in 吗？好，你们可以。你看我sign不到，不是你的问题。Yeah, doesn't matter. 我帮你们点了今天。So let's see why you are learning this epsilon delta thing. Who did it?
And it made sense to a lot. That ever lived worked. I'm in Berlin, Germany, and what you're looking at is Humboldt University. And when you know it, that Carl Weierstrass passed through these doors right here. Okay, they're technically gates, but just imagine that you're a student here at Humboldt University and you're taught by the one and only Carl Weierstrass. He's the father of modern analysis. He's known for the W function, in other words, the Weierstrass function, and he's also known for the delta epsilon technique that we see in calculus. You see, back in the day, Newton and Leibniz had their calculus, and they did make it work, and it made sense to a lot of people. But Carl Weierstrass made the definition true. I'm talking the limits exist, and this makes sense for the derivatives. And now we can understand that as we take the limit as n approaches infinity of infinitely many rectangles, then we have the integral. All these make sense, especially with the delta epsilon definition for limits because of Carl Weierstrass. But let's not forget that he made Weierstrass substitution super powerful, which transformed a trigonometric function into an algebraic one, and we can solve that using various techniques. But anyway, that's all to say that if you're in Berlin, you got to geek out, man. You got to be a math nerd and appreciate people that walk through these gates.
Yeah. So maybe one of you can do some more do on this Carl Weierstrass. Yeah. I mean, before Weierstrass, there's a lot of people working in calculus, right? For example, Newton, Leibniz, and then Riemann. Riemann also have a very great contribution there. Okay, but then why you have this modern definition is because of Weierstrass.
The first thing I see is the definition of sine.
Sine function. Okay. Yeah. Maybe someone can research on this guy. Very interesting. This university still exists, by the way. Maybe you can go and study there one day. It's Germany. Okay. All right. Cauchy. You want to do lim sup and lim inf? Huh? Should we do later or what do you think? Are you boring or not with this sequence thing? I feel like quite boring for now, because I'm repeating what I'm talking about last. How about we do link soon next time? But we do continuous function first. What do you think? 什么？烧完这个 chapter 先。哎，听不懂。
哦，一个 chapter 才 MG chapter 3。你 open chapter 3要看你。
Okay, so the flow is like this. So either we can do this lim sup lim in first, or we talk about continuous function a bit. Then tomorrow I talk about lim inf and lim sup again. 穿插。What do you think? 不然我感觉很闷，又是那个 subsequent，又在那边选三下，又选那个点，我觉得很闷。是啊，I mean like the idea 很闷，我一直重复3个钟的 idea。不然明天再讲一下，可以再 refresh 你的 idea on 选那些东西。OK 啊 ，OK， 好。Then let's start new stuff first, and then tomorrow we can come back to lim inf and lim sup. Because I'm not going using the lim inf and lim sup yet. Okay, so can jump that first. And then tomorrow I use it as a revision as well. Revision and concept. Okay. So maybe we can jump a bit further into chapter 2 now. So we have a limit of sequence already, and then idea of supremum. Now we're gonna talk about the limit of function, and then continuity of function. Okay. So we jump from sequence to function now. So sequence is like discrete, right? Now we talk about function. Not as discrete anymore. Okay, it could be discrete, but not as discrete anymore. So let's define a function. Hey, should we define a function? Okay, everyone not agree with function definition yet. Okay. So a function. Well, I mean multi-value, right? Usually we call it a Riemann manifold. Yeah, Riemann manifold. But then usually function is not multi-value. Okay, so a function f defined on the domain df on R. What does it mean? So it means that for every element in your df, I should give you a unique real number. That's it. Unique real number. Fx. Okay. In R. Okay, makes sense. So here the domain here I didn't specify, so it could be n, could be z, could be whatever thing. But then the codomain I said is specified. Okay, so sometimes this function is called a real value function. Okay, so it takes value in real numbers. So sometimes it's called real value. Yes. Yeah, output. Codomain. Variant. Yes. Instead of okay, of that, right, I will say that let me think. Okay, I'm not using variant in my class. I'm not using that. So I will avoid that confusion.
But then instead, what I would do is let me think about it first. Okay, instead what we're doing is of a df variable like that. Df variable. Okay. A real value function of a df variable. Or sometimes in calculus you will see that a real value function of a real variable. I'm not using variant in this class. Okay, so we can avoid that. Fusion. Maybe you can give me some example of function that you know. What function you know? X plus 1. Fx equals to x plus 1, huh? Okay, so in this class, it's not enough to specify like this. You need to tell me the domain and codomain. R to R. Okay, so for example, R to R. Maybe I teach you another way to write this functions. We can write it more simple, sending this x element to x plus 1 like that. Okay, this one more clean. No need to write x. Any more function that you know? There's an identity function you should always know, right? Yeah, x go to x. This is the identity function. Okay. But geometrically, do you know what they are doing here? So x to x plus 1 is like shifting up. X, and then so it's linear function x. Okay. So there's a meme, maybe I can show you. I'm not sure you see before or not. Maybe give you a head of what we're gonna do, which is this. See this meme before? Too small. Okay, here, maybe like this. Right, so this is like the high school, right? Or preview, foundation, whatever. Okay, so this is the last level. Big brain.
Actually, the last one is still not.
What else is a big brain?
Because it assumes FX and FC and C's. So you need to define what is F. So maybe you need relation, you define F as a relation, and then you define.
Oh yeah, sure. We already settled that.
And then you
Yes,
something like this. I think continue to make it more complicated. Like
Okay, cool. We already did that. So we are focusing on the continuity. But then this point here is very interesting. Later on, you might see something not as what this. This says that if you can draw it without picking out your pencil, right? So meaning continuous is like you have to go on that without. But then later you will have some examples that maybe challenging this concept. Yeah, we will see some examples. Some exotic examples that's continuous. Might not as continuous as you think, but then it is continuous. Okay. So because we define limit of a sequence, right? So we will start from there. Okay, we will define limit of a function using sequence as well. So maybe we make some observation first. Observation. So let's take a continuous function that you like, that you know that is continuous from previous knowledge. And then I invite you to think about this. Okay, so you take a convergence sequence, okay, AN to P, and then you look at what is FAN. Okay, so what do I mean by that? Okay, let's draw it. So this is a function, right? So we should be able to draw it on R2, a real value function of one variable. So let's say your function looks like this, continuous. Draw it without picking out the pencil. And then you have a sequence. let's say A1, A2, A3, right? But then you need to converge, right? So converge to some point, maybe converge to some point P here, right? And then you look at what is FA1, FA2, FA3, FA. So what are these? You evaluate it. So FA1, FA2, right? And then like that. FP. So what did you see? What did you see? When A1 getting very close to point P, this FAIA2, right? Then you also get very close to something. Okay, later I'll comment on that. But did you see that FAN converge to FP? Again, FAN converge to FP. Okay, so in fact, this is true for any continuous function. Okay, and convergence sequence. And you can do weird convergence sequence, or you can do like this, you know. You know what I mean? So you pick A1 here, A2 here, A3 here, A4 here, A5 here, A6, then converge to P. And then you can see that this sequence also converge to P. Get what I mean? Okay. Okay, so this is how we're gonna define continuous. This is the first definition we're gonna make. A function f is continuous. So we only check for a point first, at a point P, at a single point P, if for every sequence Sn, okay, that you pick from your domain, such that Sn converge to P, then the sequence of Fsn will also converge to Fp. Okay, so when we say a function is continuous, it means continuous at every point inside the domain. So really, when we say continuous, right, we have to check at a point first. Okay, if you want to say that the function is continuous everywhere, then you need to check at all points. So all points will have to check for all sequence. There's a lot of things to check. Yes,
I disagree for definition.
Okay,
Why? Because you didn't check the domain whether it's like how would say like
conversion.
It's like it's not discrete something when it's like for example if the domain is consider the domain is like
Z
rational numbers.
What you are talking about domain being not be continuous?
Yeah.
No lah, I'm continuous only defined on function. I don't know what's your usual. My usual is this. My usual is this.
It's like the epsilon delta thing.
Oh yeah. Later we can prove equivalence between these two. Obviously, yeah. Doesn't matter. No, right? I think like what we mentioned last time, right? It's rational number might not have limit living inside rational, right? So you need real. Okay. So maybe your question is, do we really need to restrict our domain to real numbers? I think this is your subset of real numbers. Huh? No? Yeah. Domain, huh? Let me see. Do we really care about that? Okay, sorry. I think something wrong here. I think this on here is a subset, I guess. I think this domain is just a subset of R. But then obviously we can generalize to different domain, but then maybe we'll run into limit problem. But then let me see my example first. Did I have some example that's not real? Okay, for now don't have. Okay. Yeah. Okay, makes sense. Sure. But then like my open interval can be empty one actually. But doesn't matter. But what matters here is maybe you are concerning whether our DF is a subset of R or not. So let's make it into R. Make it into R. Not equals R, but then a subset of R. Is it? Subset of R. Yeah. Subset of R. Subset of R. Okay. Like that. Subset of R. Okay, so okay, very good. Got improvement. Good. Very good. Yeah, subset of R, but then still will include those discrete things, but it doesn't matter. Okay. For now, at least. I think doesn't matter. Okay. So any remark I want to make here? Okay, never mind. This remark is very boring. Okay. Maybe one remark is very important. So if you want to show that the negation of this segment, then what do you need to do? Not continuous. So for all become that exists. Okay, so there exists a sequence such that Sn converges to P, but then Fsn doesn't converge to P. Fp. Okay. Like that. Okay. So how about let's look at some examples to show this to use this definition here. Maybe let's look at this example. Okay, so maybe I write down this definition. Can you try and draw this? See what do you get? This piecewise function here. Can you try and draw this piecewise function? Draw this. What's the picture? So you have two linear graph, right? Okay, one of it stop at 1/2. The other one start at 0 when x equals to 1/2 and then go up again. All right, agree? Everyone agree with this picture? Okay, if you don't agree, you should ask, because this is a basic. So maybe first task to you is to show that f is not continuous at x equals to 1/2, but is continuous everywhere. Okay, in between 0 and 1, but not 1/2. 0, 1, throw away 1/2. Yeah, like that. Okay, so just now I said that if it's not continuous, right, you need to find a convergent subsequence that converges to 1/2, but then of that sequence is not converging to. So f/2 is what? F/2 is what? F/2 is. So can you find a sequence that converges to 1/2 or not? Can you create one sequence that converges to 1/2? Any idea? You have to come up with a sequence that converges to 1/2 first. So first part, find sequence an that converge to 1/2, but have an don't converge to f of 1/2, which is 0. Okay. Give me a sequence that converge to 1/2. Give me first. Then we can check. Do things part by part. Give me a sequence that converges to half. Negative f squared. What do you mean that would be f squared? X squared. This one can converge to half again. I mean, I need a sequence. So you need to define your an such that it converges to half. Use your limit law or whatever. Right. How? Give me a sequence. Right, you can see that I give you question, you can come out with an example, right? So come out with an example is pretty important. Okay, so when you do question, right, you need to think why this question works. Okay. Any idea? What sequence can converge to half? No need the weird one, you know. You know something can converge to 0, right? There are some sequence that converge to 0, right? So why not? Huh? How's your analytic number theory? Later we're gonna define the log n for him. Seriously, I use log n. 没有人要阻止他。I mean, there's easier one in our class, right? 1 over n, 1 over n plus 1, 1 over n plus 1 also can. Right. So maybe you can consider half plus 1 over n plus 1. Right? Okay, minus maybe. Okay, so maybe you can ask a question, does this converge to half? No, man. This is a constant sequence. You can view this as a constant sequence, right? This one converges to 0, so half minus 0 is 0. But then, is these terms really living inside our domain? So meaning, are they living inside 0, 1? Is this the right sequence we want to see? Come on, 0, 1. Yeah, our domain is 0, 1. Yeah. Come on. Is that right? So if you put 1 here, you get 0. Put 2 here, you get something in between 0 and 1, right? And then so on. Okay, maybe I can rewrite this. Maybe you should ask yourself whether half minus 1 over n plus 1 is in between 0 and 1. You need to verify this. Okay, or less than or equal actually. Is it true? For all n, that is greater or equal to 1. True or not? This is true. You know how to check? Suddenly forgot how to check. Well, I mean, like, you should rewrite this, right? As negative half less than or equals to negative n over 1 over n plus 1 less than or equals to half. And then you turn things around, right? Basically, it's the same thing. And then you invert, right? So, and then you check that n actually have to be in between -3 and 1. Wait, am I doing stupid thing here? I forget to change this, is it?
Yes.
Wait, I'm a bit crazy. Wait, so, oh, right. So here, forget to change. So here, change first, and then I change again. Is that right? Huh? Wait, let me see what am I doing here. I put a negative, right? I swap this sign, right? And then I invert, right? Which one? Which one? Which one?
Because A greater than or equal to B, and then you do AC greater than or equal to B. A greater than or equal to B, and then solve the A inverse is less than or equal to B inverse. This not only works if both are positive or both are negative.
Which one is wrong? Which inequality? Which equivalence wrong?
Second last one, second last one, second.
This one.
Second.
Oh, second last one. This one.
Yeah, and then the second A.
What's wrong here? Let me see.
A is first when A is greater than or equal to B, and then you do A inverse less than or equal to B inverse. This only works if both A and B are positive or both A and B are negative. This is a restriction.
Let me think. Okay, maybe if I write. Okay, so let's write. Okay, I think you are probably right because I see very weird things here. So how should I do it? So less than equals to. This one will get n greater or equals to -3. Right. Is that right? For the other side. So on one side, I get this, right? And then this side, we get 2 move up. And then this one move up. And move here. -1, -2, -3. Right? And then the other side, I will get n greater or equals to 1. So I get both these one. Okay, so just now, what's wrong with me just now? Let me see. So what I write here is I straight away do n plus 1 less than equals to -2, right? And then n less than. Oh, one's negative, one positive, it cannot be there.
Positive reciprocal still positive, negative reciprocal still negative. How can you solve it? Very good, very good. I thought you taught it in the
That's right. That's right. Yes. Exactly. So this part is very important, right? Last time the part we say the consequence of real numbers, right? So where is it? Yes, I think you are right. So this condition here very important, right? Here. See. Okay, this condition very important. Okay, otherwise it won't work. Otherwise you'll get something very weird. So this is mathematics, so I would say. If you jump into wrong stuff, the stuff will look very weird to you. But then this is not always how you check, because sometimes your sense is not right. You know what do I mean by that? Is that maybe that stuff is wrong, but you cannot sense that thing. So still, statement is very important. Claim is very important. You cannot just rely on instinct. Sometimes instinct doesn't help. But just now, okay lah. See very weird thing, but then not always. Okay, so you get these two conditional, but then you always get the first condition. And then first condition will imply the second condition. Okay. Good. Okay, everyone okay? Okay. Okay. So maybe one moral from this question is don't when you see this kind of thing, right, don't be afraid, because this is just what you're gonna do. Right? It's just that we phrase it in a different way. And we say it is inside the interval instead of saying that it's bounded above or below by something. Okay. In that case, for continuity, maybe we left for next time. Okay. Yeah. Okay, does it make sense for now? Yeah. Maybe one exercise you can do is try and figure out, maybe you can give another example of sequence. So that it doesn't converge. Hey, have I shown you? I haven't shown you finish this example, right? So maybe I should compute what is fxn for you. Maybe there's a reason why I do this, why I pick half of 1 over n plus 1. You know why I pick this? Because half minus 1 over n plus 1, where is the terms? Actually, all these terms will live on the left-hand side. So if it is living on the left-hand side of half, I'm just using the first part of this definition. So fxn will be just okay, so fxn is just fan here. An, I will use an. Okay. Fan here is just an, which is half minus 1 over n plus 1. But then this thing will converge to half. Okay, so actually, we are picking this line here basically. Okay, we'll converge to this half. You won't jump down here. Okay, makes sense? So from this picture, if you pick your an over this side, right, then you will have something wrong because your fan will definitely go to 0. Okay. And then it doesn't meet your purpose. So one observation you see here is actually right limit exists, left limit doesn't. There's an idea that we can introduce here.
What left limit doesn't? Left limit exists.
Sorry. Left limit equal to the value at that.
That's what that's why you think.
Yeah. Left right limit exists, but then right limit equal to the value of f at that. But then the left one doesn't. Thank you. Okay. Any question? No question. Okay, then we'll continue with this example tomorrow. Tomorrow, yeah. Okay, see you tomorrow.